SwayamPrabha. Digital India. Educated India.
Hello, I welcome you all in this course on refrigeration and air conditioning, and today we will discuss the actual vapor compression cycle. We will be covering the Ewing's construction, and that is very interesting, effect of operating conditions, vapor compression cycle with reversibilities. Now, in a typical vapor compression cycle, if we draw on a pressure enthalpy diagram, if there is wet compression, it means the vapor is saturated after the compression, and at the inlet of the compressor the vapor is not saturated, it is a wet vapor. Now, in this case, if I keep on increasing the temperature of 1, if I keep on increasing the temperature of 1, or this state 1 will be start shifting here, then I will be getting vapor superheated after the compression. If we further shift it, again I will get vapor superheated after the compression. Now, here the issue is, if I keep on increasing this temperature T1, I will be getting more refrigerating effect. Refrigerating effect will increase, and at the same time compression work will also increase. Now, the issue is, what is the benefit? Benefit means how it is going to affect the COP of the system. COP of the system is the ratio of refrigerating effect and the work consumed by the compressor. So, since we are shifting state 1 to the right side, refrigerating effect is increasing and work is increasing, there should be one optimum value of the quality of vapor at the suction of compressor, which will give the maximum COP. Because the moment we shift in this direction, because these constant entropy lines are diverging lines. So, the moment we shift in this direction, the work consumed by the compressor increases. Now, Ewing's construction gives solution to this problem. Now, if we transform this pressure enthalpy diagram on Mollier diagram, this is Mollier diagram is enthalpy entropy diagram, and that can be drawn for any gas or any vapor. So, for example, for a refrigerant R134A, if I draw Mollier diagram, this is the saturation line. Below this I can get different saturation lines for different qualities. For example, x is equal to 0, x is equal to 0.9, x is equal to 0.8, and so on. Constant pressure lines can be shown here as these lines parallel, they are not parallel, these lines, these are constant pressure lines. So, in a PV diagram, pH diagram of any refrigerant, these are constant pressure lines. So, state 1 to state 2 can be shown here as state 1 to state 2. Entropy is remaining constant, that is why it is a vertical line, and state 1 to state 2, the change the change in entropy is 0, and it is going to be a vertical line here. Now, state 2 to state 3 is a constant pressure line. Definitely it is going to come here, state 2 to state 3, and it is in liquid state. This is also here, also it is shown in the liquid state. Now, state 3 to state 4 is constant enthalpy line, enthalpy is constant. So, constant enthalpy line in this case is going to be a horizontal line. So, this is refrigeration cycle on transformation of refrigeration cycle on enthalpy entropy diagram. Now, in this enthalpy entropy diagram, if I want to find COP of the system, then the COP of the system will remain same, that is refrigerating effect H1 minus H4 divided by work consumed by the compressor. Now, we can do further manipulation in this equation, and we can further write this equation as H1 minus H4 divided by H2 minus H4 minus H1 minus H4. Both equations are same. Divide now by delta S. Delta S is change in entropy. Delta S is change in entropy. Delta S. So, here we can write that H1 minus H4 divided by delta S divided by H2 minus H4 divided by delta S minus H1 minus H4 divided by delta S. Now, H1 minus H4 divided by delta, this is a constant pressure line, and during this process the temperature also remains constant. If you look at the pH diagram, this process the temperature remains constant. So, during process 4 to 1 temperature remains constant, that is why change in enthalpy divided by change in entropy shall give the temperature during this process, that is TO. Here also we can take H2 minus H4 by delta S minus TO, and this is equal to COP of the system. This is equal to COP of the system. Now, here in this case, the COP is going to be maximum when this is minimum, because TO is fixed, TO cannot be changed, but we have to ensure that this is minimum. In that case, this expression means H2 minus H4, enthalpy of the vapor after compression minus enthalpy of the vapor after expansion or at the entry of the evaporator, divided by delta S, because in this process delta S 0, in refrigerating process, that is state 4 to state 1, the delta S is this much. So, H2 minus H4 divided by delta S has to be minimum. Now, H2 is here, H2 is here, this is H2, and H4 is here, H4, this is delta S. If you look at these values, this is nothing but the slope of this line. If you connect 4 to, it is slope of this line. If we can minimize the slope of this line, because this is also shown here as a straight line, but basically it is not exactly a straight line, it is a slightly curved. So, this line is something like this. So, this slope of this line has to be minimum, in which case it is going to be minimum when we draw a tangent from here. If we draw a tangent from here, then this point, this is 2m, let us say 2m, this point, and then we draw a vertical from here, this is 1m. Now, process 1m to 2m, if we adopt the cycle or if we modify the cycle as 1m, 2m and then 3 and then 4 and then 1m. In this case, this cycle will give the highest COP. Reason being H2 minus H4 divided by delta S is minimum in this case. Now, if we further increase the quality, we can come up to here, then we will be getting 1s, from 1s to 2s. But in this case, so this value of 1m is different for different refrigerants. In some of the refrigerants like ammonia or R22, it is in the wet region. In some of the refrigerant, it is in superheated region like R134A, but ewing constriction has limitation, it is valid up to saturation state. So, if we look at the R134A, we will find as we are going from this point to this point, the COP of the cycle is increasing, because for R134A the maximum COP is attained when the vapor is slightly superheated. So, that process is I am not covering that process here. Instead of that, I would like to cover the effect of operating parameters on the performance of the cycle. Now, we are very well familiar with the vapor compression cycle. Now, we will discuss effect of different operating parameters on vapor compression cycle. Now, a vapor compression cycle on pressure enthalpy diagram is already shown here. In the previous lecture also we have amply discussed the pressure enthalpy diagram, but here I would like to again repeat it, that in pressure enthalpy diagram on the vertical axis there is a pressure on megapascal. This axis is on a log scale. On the horizontal axis there is enthalpy kilojoules per kg or specific enthalpy. There are horizontal lines which are constant pressure lines, obviously there are vertical lines which are obviously constant enthalpy lines. There are certain inclined lines also, they are constant entropy line in this chart. This chart also has constant temperature line, for example -30, so -30 this is almost vertical, this is not vertical but almost vertical, then it becomes horizontal because during phase change the temperature remains constant. This thick line curve, this thick curve is saturation curve. Beyond this side, beyond this or on this side of the curve there is superheated vapor, on this side of the curve there is subcooled liquid, on this curve on the left, on this side of the curve there is saturated liquid, on this side of the curve there is saturated vapor, and both the curves are joining here. This is the critical point. Beyond critical point there is no liquid phase. Now, this is a typical cycle which is shown here having wet suction. So, after the compression the vapor is saturated, condenser temperature is 40 degree centigrade, evaporator temperature is -20 degree centigrade. Now, here in this case if I reduce the temperature, instead of 20 degree centigrade temperature, if I reduce the condenser temperature or condenser pressure to -30 degree centigrade, it means now before doing that I would like to take a cycle which has vapor, saturated vapor at the suction of the compressor. So, we are going to get this. So, B will be shifted here, A will be shifted here. So, this is going to be the cycle which we are going to analyze. In this cycle the vapor is saturated at the suction of the compressor. After the compression the vapor is superheated, condensed up to the saturated liquid, and isothalpic expansion takes place during process C to D. Now, if I transform this cycle on pH diagram or in a separate diagram, it is going to be like this. Now, in this process suppose I reduce the evaporator pressure, correspondingly the temperature will also get reduced. Now, if I reduce the evaporator pressure, in that case what is going to happen? In that case we are losing this much of refrigerating effect. The length of this line will reduce. So, if I extend it up to 30 degree centigrade, then we will be losing this much of refrigerating effect. So, when we reduce the condenser pressure, evaporator pressure, the refrigerating effect is reduced. That is first thing. Now, the second thing is, what about the compressor work? Since we have reduced the evaporator pressure, the compression process will be shifted to this one. Now, B will be shifted here. B will be shifted here. If I show it here, then it is going to be like this. This is 1, this is 1 dash. Now, you can see from here itself the compressor work has also increased when we reduce the evaporator pressure. So, when we reduce the evaporator pressure, we are loser at both ends. First, the refrigerating effect is reduced. Earlier it was 4-1 here, now 4-1 has shifted to for 1 dash. So, 1 has shifted to here 1 dash. So, refrigerating effect has reduced. At the same time, the compressor work has increased. So, we are loser at both the ends and COP of the cycle has to go down, or it will reduce, definitely reduce in this case. Now, the third is when we reduce the pressure, the density of the liquid is also reduced. If you look at the density here, it is approximately 6.5 here at minus 20 degree centigrade, approximately. This is 6 kg per meter cube, this is 8 kg per meter cube. So, it is approximately 6.5 or 6.3, but when we reduce the pressure, the density will also reduce, it drastically reduce, it will reduce to 4.5 or 4.3. When the density of the liquid which is entering the compressor is reduced, volume of the compressor is constant, volume of the compressor is constant. When the density of the liquid entering the compressor is reduced, the mass of the refrigerant which is entering the compressor is reduced. When the mass of the refrigerant which is entering the compressor is reduced, it means mass of the refrigerant which is being circulated in this cycle is also reduced, and that will also reduce subsequently, which will also reduce the refrigerating effect. So, when the evaporator pressure is reduced, in that case refrigerating effect is reduced, compressor work is increased, mass of the refrigerant which is being circulated in the cycle is also reduced due to change in density. And further, if you look at the expression of volumetric efficiency of the cycle, that is 1 by minus epsilon P2 by P1 raised to power 1 by n minus 1. Now, if you look at this expression, if we increase the pressure ratio, the volumetric efficiency will also reduce. So, here in this case, if we reduce the pressure of evaporator pressure, the volumetric efficiency will reduce. So, we are loser at all the fronts. We are loser at all the fronts, refrigerating effect is decreasing and pressure is this volumetric efficiency is decreasing, work consumed by the compressor is increasing. So, we are loser at all the fronts, that is why in any case if the pressure of the evaporator is reduced, the performance of the system deteriorates. Now, the second case, when the pressure of condenser rises. When the pressure of the condenser rises, now let us take again the original cycle, and now instead of reducing the pressure of the evaporator, the pressure of the condenser is increased. When the pressure of the condenser is increased, here compressor will consume more power, compressor will consume more power. This is the additional power which is going to be consumed by the compressor. At the same time, refrigerating effect will be reduced. Earlier we were getting 4.1, now we will be getting 4-1. So, when we increase the condenser pressure, the refrigerating effect is reduced and the compressor work is increased. Again, the COP of the system will be reduced. That can be shown here also. Say instead of 40, suppose it is compressed up to 50 degree. So, when we touch the 50 degree, then here you can see the refrigerating effect will reduce. Earlier we are getting refrigerating effect out of this, now we are getting refrigerating effect out of this process, and at the same time, here we are getting refrigerating out of this process, earlier we are getting out of this, and at the same time compressor work is also increased. Now, the third case, if we superheat the gas, instead of taking saturated vapor, if we superheat the gas, and then during superheating in this process, the refrigerating effect will increase because the gas which is coming out of the evaporator is superheated, and at the same time compression work will also increase. At the same time the compression work will also increase in comparison to this 2, 1 dash, 2 dash, in comparison to the process 1 to 2. So, in 1 dash, 2 dash process the work will be more than process 1 to 2. So, but in superheat the COP of the system may increase or may not increase, it depends. I have told you earlier also, if you look at the EVX construction, for some of the refrigerants like R20 or ammonia, the maximum COP is when the vapor is wet at the suction of the compressor, and for refrigerant R134A, it has been found when the vapor is slightly superheated, the COP is maximum. Now, for fourth operating parameter can be subcooling of the liquid. If we do subcooling of the liquid by external means, so if we are able to do subcooling of the liquid through external means, definitely refrigerating effect will increase, because this cooling, if let us say 40 degree centigrade, the vapor is subcooled. So, now this subcooling we are getting free of cost if it is done with the external means. However, as I stated in my previous lecture, this subcooling can be attained by superheating the vapor coming from the evaporator. In this case again, for getting this subcooling, we are superheating here and more power will be consumed by the compressor. So, if we are doing superheating with the help of vapor coming out of the evaporator, in that case we are getting more refrigerating effect, and at the same time more power will be consumed by the compressor. Now, after this I will take up vapor compression cycle with irreversibilities, because the actual cycle, in actual cycle the processes are not reversible, all the processes are irreversible, and that is very important to understand how the system behaves in actual practice. Let us transform the vapor compression cycle on pressure and enthalpy diagram, and we will start from the point where the vapor emerges from evaporator. Now, evaporator is connected to the compressor through a pipeline, and vapor which is coming from the evaporator is approximately at, let us say, if the evaporator temperature is minus 20 degree centigrade. So, this vapor is at minus 20 degree centigrade, right. This is state 1. But when the vapor enters the compressor, it picks heat from the surroundings and it gets superheated. So, vapor will get superheated. So, we will get 1 dash, right. Now, this is constant temperature lines. So, minus 20, maybe it may attain minus 18 degree centigrade. Okay. Now, this superheated vapor enters the compressor, and during this process, flow of vapor from the exit of the evaporator to the entry of the compressor, there is a friction loss. So, there is a friction loss in the pipeline. So, we get A double dash. Further, when the vapor is entering the compressor, there is a pressure drop across the compressor wall, because when the vapor is entering the compressor, pressure in the pipeline is higher than the pressure inside the compressor. So, this pressure drop takes place across the compressor wall, and we get, let us take A1, 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 A, and sorry 1A and 1B. So, we get state 1B. I am repeating here that vapor coming from the evaporator is saturated. In the pipeline connecting the evaporator to the compressor, the vapor gets superheated, right. We get state 1A. Then there is a pressure drop in the pipeline, we get 1B due to friction, and then here we get 1C in the inside the compressor, because there is a pressure drop across the compressor valve also. Now, compression takes place, and this compression is also not isentropic, there is a polytropic compression. In polytropic compression, there is a, it is not a curve, it is PV raised to power n, and during this process heat transfer also takes place. Earlier we have assumed that it is isentropic compression, there is no heat transfer across the boundaries of the compressor, but in this process 1 to 2, let us say 2, the heat transfer takes place across the boundary of the compressor. Now, after this polytropic process, the vapor comes out of the compressor, and this is condenser pressure. So, the pressure inside the compressor or at the exit of the compressor should be higher than the pressure in the pipeline which is connecting the condenser, otherwise the vapor will not go into the pipeline. So, this pressure, so the pressure at the exit of the compressor can be denoted by 2 and pressure drop takes place across the compressor wall. And this line is not a horizontal line, it is an inclined line because the pressure drop takes place during this process 2 to 3. Now, the vapor coming out of the compressor is at high temperature. So, when it enters the pipeline, some amount of cooling takes place inside the pipeline itself because the vapor is at a higher temperature. And after this we get, this is 2A and we get 2B. From 2B to 3 the condensation takes place and during this process also there is a pressure drop, right. Normally we do not get saturated vapor at the exit of the condenser, normally it is subcooled. So, we will go up to the subcooling state, this is 3. Now, at 3 when vapor comes out of the condenser, right, it is in liquid state and expansion takes place inside an expansion wall, right. So, expansion takes place inside an expansion wall and we get state 4 and the pressure of state 4 is higher than the pressure of state 1. And it is also possible that some heat, the liquid may pick some heat from the surroundings and some heating takes place and we get, instead of 3 we get 3A here. Expansion takes place in an expansion device and then 4 to 1, process 4 to 1, again the pressure drop takes place in process 4 to 1. Now, here in both the cases, in evaporator and condenser, at both the places the pressure drop is taking place, but in 4 to 1 the pressure drop is more severe or more of concern because here the pressure drop is due to friction in the flow and there is a pressure drop due to momentum also because the velocity, the vapor is getting vaporized and the fluid is picking up the kinetic energy and it is picking up the kinetic energy at the expense of the enthalpy of the fluid, right. So, they have cumulative effect and there is a large pressure drop in evaporator. However, in the case of condenser, condensation is taking place or the kinetic energy of the fluid is reducing, which is being converted into the pressure energy. So, pressure should rise here, but at the same time pressure loss is taking place due to friction, okay. So, both these effects are compensating each other and sometimes it happens that there is a pressure rise in the condenser, but normally it does not happen, but this can also happen, there is a pressure rise in the condenser. It means the conversion of kinetic energy to the pressure energy is more than the loss in the friction of loss of pressure during in the friction. However, in the case of evaporator, the pressure loss, they have cumulative effect and there is a substantial pressure drop in, and it affects the performance of the system also because the T4, these are two different temperatures. Suppose this is minus 20, this may be minus 15. So, this also hampers the performance of the system, but this is the actual vapor compression cycle and that is why the actual vapor compression cycle has COP much lower than the COP of an ideal vapor compression cycle. So, we have discussed the real or the actual vapor compression cycle with irreversibilities. We have completed the vapor compression cycle with irreversibilities and now in the next class we will go for a multi compression system with intercooling.